Hello students, so once again we are back and today we are going to discuss about the principle of feedback control design. In the principle of feedback control design, it is just a part of the feed flow pole placement design. In the pole placement design, we have already established the concept what is the need of the pole placement design. As you know that the location of the dominant pole decided by some performance index, and those performance index is simply defined as a rise time, rise time, settling time, peak time, right? Peak time, settling time, and the peak overshoot, right? Peak overshoot, damping ratio, right? Damping ratio, and natural frequency of oscillation, that is the omega n, natural frequency, right? So these parameters will decide the location of the poles, right? So as you know that if the location of the dominant pole lying in the left half of this plane, if it is lying far away from the imaginary axis, if your dominant pole if your dominant pole, we already discussed these things, if your dominant poles lying in the left half, right, left half, and also this is the lying far away from the imaginary axis. What it means? It implies your response will be faster, right? It implies your response is faster response, okay? But at the same time, the frequency of oscillation is higher. Frequency of oscillation is higher, right? And if the dominant pole is located, let's say, near the origin, near the imaginary axis, if your dominant pole located, you can say, near the imaginary axis, then what it implies? It implies your response will be getting slower, right? Will slower and sluggish, right? And for the effective change in the system response, it is sufficient to change. You have to change the location of the poles, right? So for that purpose, you have to change the location of the closed loop poles. So to some desired location, to some desired location, right? So in this way, you have to shift the poles from one point to another point as per your desired performance indices, right? You can say. We have also seen one example in the case of the pole placement. That example was just I'm once again I'm establishing the concept so that you can connect the new topic what we are going to cover today. So let's say we have the one damping ratio of one problem 0.5, and let's say the settling time is given as the 2 second, okay, 2 seconds. So you can see here the settling time is usually given by the 4 upon zeta omega n, and this is the 2 seconds. So you can calculate the omega n, and omega n will come as a 4 radian per second, right? And now what is the pole location? So you can simply calculate the s square plus 2 zeta omega n. This is a characteristic equation of the of the system of the plant, and this will give s square plus 2 zeta. So zeta is 0.5 and 2 is 2 into 1, and it becomes 4s plus 16 equal to 0. So s, the location of pole, is nothing but the minus 2 plus minus root under j root under 12. Sorry. So this is the location of the pole where now as per the settling time and the zeta, the location of the pole is here. Let's say now it is desired we want to change the tangent response. Let's say we want to change the settling time 2 second to 1 second, right? 2 second to 1 second with same zeta value. With same zeta value means 0.5. So it means your transient response will change, and let's say now your ts, that is a modified, it is a modified, okay, ts modified, that is the 1 second, and it is given by 4 upon zeta omega n, zeta 0.5, and omega n, it is a modified again, right? So it will given the 1. So you can calculate the omega n modified, and it is nothing but your 8 radian per second, right? So your new characteristic equation as per this omega n, s square plus 2 zeta omega n modified, right, plus you can say the omega n square, that is a modified, equal to 0, and it will come the s square plus 8s plus 64 equal to 0. And when you calculate the s, it will come minus 4 plus minus root under j4 root under 48. So what it mean? It mean your poles is going to change when you are saying that your your performance index you want to change. Suppose that one of the performance index is the settling time. If you want to change the settling time, then your automatically the poles of the location of the poles get changed. And also it is verified that as you going you can say far away from the imaginary axis, your response becomes faster because settling time becomes 1 second from 2 second by 2 second, right? From 2 second it reduces to 1 second, and therefore it is also verified that as you going from far away from the imaginary axis, your response is going to faster. Okay, so this is the beauty of the pole placement design, and we already have discussed up to this point. Today we are going to discuss the principle of feedback controller, and I'm always repeating and appealing to my students before my lecture. Just you revise whatever I have taught you, because you can only connect me the concept, only you can connect when you are going through the previous video. Okay, so it is my request to all of these students, please go to the previous video and try to establish the concept, because concept is very very important. Okay, so today we are going to understood the principle of feedback controller design, and in this design problem, let's consider we have a plant. Consider a plant of that is again represented by some state equation, and some state equation is, you know, that so simple state equation is ax plus bu and y is equals to cx plus du, right? Cx plus du. Okay, so what is the eigenvalue? The eigenvalue, the how the eigenvalue calculated? Eigenvalue of the above plant or of above dynamics may be calculated as, you know, simple a si minus a equal to 0. Okay, si minus a equal to 0, and also let's say we have you know, consider, you can say consider that each state feedback, each state variable is feedback to input signal. It means suppose that we have all the input signals available, for the feedback, and it measures your state variable. All the state variables can be measured with all the input. So it means, let's say, simple fundamental, you can say that we have the input R, okay, and let's say we have some F here, okay, and let us some feedback is coming from this side. Okay, sorry. and let's say we have the B mat block, and here it is the, you know, x dot, and this is the A. As you know that it is very easy, we already have discussed these things, so I think there's no need to repeat once again. Here this is the x, okay, and this is the C, okay, and you know this is the forward matrix, और यहाँ पर हम क्या, this is the, this will be the D. Is that clear? I think. Okay, so we have this a plus, and from this side you have a K matrix, and this K is important. Our target is to design this K in this picture. This is the UC. Okay. Sorry. So our target is to design the feedback controller design, feedback controller K. So state feedback, okay. So we are considering that all the state variable, all the inputs are available for the feedback, and here all the states can be measured. So state feedback, you can say that the state feedback signal, state feedback signal UC is given as, UC is nothing but, you know, kx, right? This is the x. So UC is nothing but the kx. UC is nothing but the this k, and whatever the x is coming from this side, this is the kx. Okay. So this can be represented as a, like this one. Suppose that we have a number of n variables, state n variables. So it requires n inputs, and that correspond to n variable, that correspond to the nk. Okay. So k1, k2 up to the kn. Okay, and similarly the state variable is there, that is the x1, x2 up to the xn, and it will be the transpose, right? Okay, so now think this is the u, okay, this one is your u that is going to the system. So what will be the value of u? U is nothing but, you can say simple, fr minus of kx. If I'm not wrong, then you can write fr minus of kx. Okay, and you know that this is the x dot. The value of x dot, the value of x dot is nothing but the ax plus bu, and when you put the value of, when you put the value of the u, then you can simply write down fr minus kx. And when you solve this equation, when you solve this equation, you can write a minus bk, right, into x plus bf into r. Bf into r. So this is the equation. So your, now your characteristic equation was si minus a, determinant of si minus a equal to 0, when your feedback was not considered, right? When your feedback simple, when the dynamics was given, then your characteristic equation is this one, right? When your dynamics, now your dynamics with the feedback feedback is changed, state feedback when you consider, then your dynamics is changed, x dot is changed, and now you can find out the characteristic equation, your new characteristic equation, you can say. Now your new characteristic equation, now your new characteristic equation, it is si minus a minus bk, okay, equal to 0. If I'm not wrong, then it is the new equation, new characteristic equation. Okay, so with this state feedback, the new system matrix, your new system matrix become a minus bk. Your new system matrix, your new system matrix is now not a, it is the a minus bk now. Okay, a minus bk. And what it implies? It implies the new closed loop pole or the new desired location of closed loop pole, right? It means it is the system matrix is now changed. It implies your new closed loop pole. It implies it will give the new closed loop pole, new closed poles, you can say. Okay, okay, okay. This is the loophole. Okay, low close loopholes. What it mean? It mean you new desired. It is nothing but it is the new desired location of closed loop poles. Right. So now it's the time to summarize what we have studied. What we have studied. This is the summary time. And when you summarize these things, we can write here each state. Once again, each state, all the states should be available, right? Each state variable means x1 to xn is feedback, right? Is feedback. Okay. To control signal, to control signal u through we are getting from k, right? And what is the k? K is nothing but the k1, k2 up to the kn. That could be adjusted. Okay, that could be adjusted to yield the required closed loop pole, required closed loop poles, right? Hence by introducing the matrix K, that is the each state feedback, through, you can say, through pre-designed K, that is the K1, K2, right? And gain. Okay. So all the poles of closed loop can be placed at desired location. Am I right? So you can understand now. I think you have. I hope you understand it better. Right? So now it means the desired characteristic equation. Your characteristic equation is now changed. Yes or no? So now the desired characteristic equation is obtained from it obtained from some new design characteristic, right? New design specification or characteristic. And what is this specification? The specification will come? This specification will come from some performance index, as we have seen in some example, right? Your settling time is going to change from 2 seconds to 1 second. That performance indices will provide you the new target, new desired location, new desired characteristic equation, where we have to shift the location, right? So the characteristic equation with feedback given is compared, then with you can say the desired equation to evaluate the value of k. So this characteristic equation, the previous characteristic equation, right, with state feedback, okay, is compared with desired characteristic equation, right? Desired characteristic equation come from the performance indices. Okay, desired characteristic equation to evaluate the value of k. We will see from one example. And this method is nothing but known as the method of matching coefficient. Okay, so this method, and very important, this method is called method of matching, right? Method of matching coefficient. So in the next lecture, we will try to cover the method of matching coefficient. Okay. So till goodbye.